We are the team that created the Microgrid control system project, and our project is basically solving the problem of peak demand charges for power generation systems in homes and commercial settings. So when you are charged for your electric bill, sometimes you may receive two main charges on your bill, charges for the amount of power you actually use, and then charges for the amount of power that the utility company has to make available to you at your peak usage time. So our project aims to kind of round out that big peak so that it is less power drawn from the grid and more power drawn from alternate sources. So in our project, we have solar panels and a battery that work with our system. In actual applications, you could add wind turbines, generators, other forms of power generation. This system is meant to be customizable and scalable to whatever the customer needs. Currently in industry, there is a big switch to microgrids, but a lot of them are focusing on the inverters. So our system is different in that all of our system is in this external box here, so it can be added on to any existing power generation system in a home. All of this outside stuff is peripherals that we're interfacing with. Our product lies in here. So this is for anyone who doesn't want to spend an extra few thousand on a brand new inverter. This can just plug into any existing system. So we have a circuit board in here that has two different microcontrollers that are gathering data and processing data from all of our different sources. We have monitoring voltage and current from all our different sources and our loads. So we have a big picture idea of where the power is going in our system, and we have an algorithm that calculates the most efficient route for all of this power to take to try and reduce that peak load. We also aim to have a non-critical disconnect so that if there was, say, a power grid outage, our system could operate off-grid, and if our system detected that we don't have enough power stored in our batteries to operate everything, we would decide what is priority or non-priority and be able to cut that so we can make sure we're keeping important things like your fridge and your heat on in grid outages. I'm going to pass you on to Connor to tell you more about our sensing.
So the brief interview into our sensing. In this application, we only have two major sources. We have our DC that comes from our solar power, which we have panels over here behind the rest of the group, and then we have our AC, which comes straight from grid. In other applications, you might have more, like you might have a wind or a backup generator, whatever you do, but our system needs to be able to monitor these power sources so that we can decide the best route for them to take to supply our loads. So each one of these has two measuring points. They'll have a voltage measurement and a current measurement, and that data is given to the controller to back calculate the power. For our AC, we use a current transformer clipped around the load line to pull our current from, and then we take the voltage off down at the load box and use a divider to find our voltage measurement. For the DC, we have a sensing shunt resistor that pulls our current measurement and another just pulling off at the voltage lines and using a divider to find our voltage. And then all that reads into the TNC microcontroller, which will read in our data and hand it over to the Pi, which is what will output our data over to our software, or our software that shows us our graphs on the laptop. For the AC, we use an A to D converter just to get everything over to the TNC. All right, I'll hand you off to Nathan. He can discuss more of the software side.
So our software stuff is actually pretty simple compared to maybe some different capstone projects, because we're essentially just communicating a TNC and a Raspberry Pi to each other. And to do this, we're utilizing a TCP Modbus. And part of the reason we chose Modbus is because it also allows us to communicate with our inverter. And that just that opens up a lot of opportunities for different types of control we can have. So as Connor mentioned previously with the signal conditioning, the TNC just receives an input that's been configured to be within 0 to 3.3 volts, which is then back calculated to get our actual voltage or current value that we want to measure. That then gets sent over to the Pi, where it's logged in a kind of an Excel spreadsheet sort of thing, and it gets time-stamped, and so you can look at it later down the line to see like how the system's performing and whatnot. We also have the ability to draw that data and turn it into like a graph so you can see real-time updates.
So for the future of this project has applications that could be in residential or commercial spaces. It can be scaled to fit any system. Ideally, it would be nice to have a little bit cleaner hardware. We definitely had some problems with our design. So it'd be great to be able to hand this off to another team in the future for them to refine everything now that we have all the peripheral stuff set up and kind of laid the framework. And even opening up opportunities to a computer science team to develop an application and potentially machine learning software to do all of the calculations for what is optimized for power generation. So there's a lot of future applications, and we can't wait to see where this project goes after we leave.